In this video, we look at the work on simultaneous equations in three unknowns required by the Unit 4 of the Further Maths specification of WJEC. So the key ideas that we've got to be able to solve linear simultaneous equations in three variables, either using the inverse matrix method or by using the method of reduction to echelon form. We need to understand the use of the determinant of the matrix in terms of what the solution of the equations will be. And we need to be able to interpret geometrically the solution or the lack of solution of simultaneous linear equations. So, key facts. First of all, we need to realise that if we've got three equations in three unknowns, then we can write it in matrix form as the matrix times xyz equals pqr, where m is the matrix of coefficients in the equations. Most importantly, if the determinant of this matrix is not equal to naught, then the equations will have a unique solution. And that unique solution is xyz equals m inverse times pqr. So the solution can be found by using the inverse matrix or by using the method involving reduction to echelon form. On the other hand, if the determinant of m is equal to 0, then the equations do not have a unique solution, and they cannot be solved using the inverse matrix method. So solution of such systems of equations requires the method of reduction to echelon form. If the determinant of the matrix is equal to 0, it's possible that the equations will have an infinite number of solutions, but it is equally possible that the equations will have no solutions at all, in which case we say that the equations are inconsistent. Geometrically, each of the equations ax plus by plus cz equals alpha, and dx plus ey plus fz equals beta, and gx plus hy plus iz equals gamma, each of those represents a plane in three-dimensional space. And when we think about the intersection of three planes, the intersection of three planes can be in a single point, it can be in a line, and indeed they may not meet at all because the planes are parallel, or there's a possibility that the three planes may end up forming a tent shape or a wedge, and hence have no point or points where all three planes meet at the same time. So let's move on and have a look at some examples. So in this question we have the matrix A is given by the matrix 2 lambda 3, 1 2 lambda 4 5 5. And the first thing we've got to do is we have to find the values of lambda for which A is singular. So there's our matrix A. Now a singular matrix is a matrix whose determinant is 0. So we've got to find the values of lambda for which the determinant of A is 0. So to evaluate the determinant, we can repeat the first two rows of the matrix A, and then we start by looking at the diagonals across our array of numbers that go from top left towards the bottom right. So the first diagonal 2 times 2 times 5 gives me 20. The second diagonal going from top left to bottom right is 1 times 5 times 3, which is 15. And the third diagonal is 4 times lambda, which is 4 lambda squared. And then the negative values that we've got come from the diagonals that go from top right to bottom left. So the first one we've got is 3 times 2 times 4, which is 24. The next one is lambda times 5 times 2, which is 10 lambda. And then the third one is 5 times lambda times 1, which is 5 lambda. So the determinant of A is 20 plus 15 plus 4 lambda squared. Take away 24 plus 10 lambda plus 5 lambda. We can tidy this up now as 4 lambda squared minus 15 lambda plus 11, and factorise that as lambda minus 1 times 4 lambda minus 11. Now, we know we're wanting to find the values of lambda for which A is singular. That means we're trying to find the values of lambda for which the determinant of A is 0. And from the factorised form, we can see the determinant of A is 0 if lambda equals 1 or 11 over 4. So the matrix A is singular if lambda equals 1 or 11 over 4. So moving on to the second part of the question, we've got the matrix A again, but we're now told that lambda equals 3. And the fact that lambda equals 3 means that we've got the matrix A is 2, 3, 3, 1, 2, 3, 4, 5, 5. And it also means that we know the determinant of A is 3 take away 1, which is 2, times by 4 times 3 take away 11, which is 1. So the determinant of A is 2. So we've got to find the inverse of this matrix A, and this requires us to go through the process of first of all finding the cofactor matrix and then the adjugate matrix of A. And this process we went through in the previous video. So going through this fairly quickly again, we start off with this grid of pluses and minuses and the original matrix. To find the first entry of the cofactor matrix, we cross out the first row and the first column of the matrix A. We work out the determinant of what is left, so that's 2 times 5 take away 3 times 5, which is minus 5. Because the entry in that original grid matrix is a plus, the entry is going to be exactly the same as the determinant, so the entry we're going to put in is minus 5. Moving on to the second entry, so we're still going to cross out the top row and cross out the second column. The determinant of what is left is 1 times 5, take away 3 times 4, which is minus 7. The entry in the grid is a minus, so the entry that we're going to replace is minus the determinant. So the entry we're going to put in is minus minus 7. In other words, the entry that we're going to put in is 7. And we carry this process on, slowly but steadily. So determinant there of what's left is minus 3. So the entry is going to be minus 3. For the next one along, the determinant of what is left is 15 take away 15, which is 0. so the entry is going to be minus 0, which is still 0. For the next entry along, the determinant of what's left is 10 take away 12, which is minus 2. The entry in the grid matrix is a plus, so the entry that we're going to replace that plus by is going to be the same as the determinant, so it's going to be minus 2. For the next entry, the determinant we've got is negative 2 again. We've got a minus in the grid matrix, so that means the entry is going to be the negative of the determinant, so in this case the entry is going to be plus 2. Next entry, the determinant is 3. The entry in the grid matrix is a plus, so the entry that's going to replace that plus is just going to be the same as the determinant, namely 3. For the next entry, the determinant of what is left is 3. In the grid matrix we've got a minus, so the entry now is going to be the negative of the determinant, in other words it's going to be minus 3. And then the final entry gives us, we have a determinant of 2 times 2 take away 3 times 1, which is 1. The entry in the grid matrix is a plus, so the entry that replaces that plus is going to be the same as the determinant, namely 1. So we've now got our cofactor matrix. The adjugate matrix is the transpose of the cofactor matrix, which means that the first row of the cofactor matrix becomes the first column of the adjugate matrix. The second row of the cofactor matrix becomes the second column of the cofactor matrix, and the third row of the cofactor matrix becomes the final column of the cofactor matrix. So we've now got the adjugate matrix for A, and then we simply need to remember that A inverse is 1 over the determinant of A times the adjugate of A. We've already seen that the determinant of A is 2, and we've just found the adjugate of A, so there we are, we've got A inverse is 1/2 times the adjugate of A. We've now got to just solve these equations, and looking carefully at these equations we notice those equations are exactly the same as 233, 123, 455 times xyz equals 2 minus 1, 4. In other words, we've got A times xyz equals 2 minus 1, 4. Now if we pre-multiply each side of this equation by A inverse, the left hand side becomes A inverse A times xyz, and A inverse times A is just the identity, so the left hand side just becomes xyz, the right hand side just becomes A inverse times 2 minus 1, 4. So we've got xyz must be the inverse matrix times by 2 minus 1, 4. So if we work out the matrix part first of all, I've got minus 5 times 2 plus 0 times minus 1 plus 3 times 4, so that's minus 10 plus nothing plus 12 gives me 2 as the top entry in the matrix. Second entry, we've got 7 times 2 is 14, add minus 2 times minus 1 is 2, add minus 3 times 4 is minus 12, so that's 14 plus 2, add minus 12, so that is 4. And then finally we've got minus 3 times 2 is minus 6, plus 2 times minus 1 is minus 2, plus 1 times 4, so I've got minus 6 plus minus 2 plus 4, which gives me minus 4. But I've still got the half from the determinant part to deal with, So when I multiply through by a half, I get xyz equals 1, 2, minus 2. In other words, I've got x equals 1, y equals 2, and z equals minus 2. Moving on to a second example, we first of all have to find the value of k for which the matrix 1, 2, 1, 2k1, 3, 4, 1 is singular, and then we have to consider a system of simultaneous equations. So let's start off with the first part, remembering that if a matrix is singular, its determinant has to be equal to 0. We can see that we've got to work out the determinant of the matrix 1, 2, 1, 2k1, 3, 4, 1. So there's the matrix, and we repeat the first two rows underneath the matrix, and then we can start our determinant calculation. So first of all, we've got the determinant, the positive terms in the determinant are going down the diagonals from top left to bottom right. First one is 1 times k times 1, which is k. The second one is 2 times 4 times 1, which is 8. And the final one is 3 times 2 times 1, which is 6. And then we have to take away the terms we get by going down the diagonals from top right to bottom left. So going from top right to bottom left, we've got 1 times k times 3, which is 3k. We've got 1 times 4 times 1, which is just 4, and we've got 1 times 2, which is another 4. So the determinant is k plus 8 plus 6, take away 3k plus 4 plus 4, which simplifies to the determinant is 6 minus 2k. If the determinant is 0, which we need if the matrix is going to be singular, then the value of k must be 3. Okay, the system of equations that we've got is exactly 1, 2, 1, 2, 3, 1, 3, 4, 1 times xyz equals 1, 3 lambda. So that's exactly the situation in which the matrix is singular. The matrix has a zero determinant. The matrix does not have an inverse. So, because the matrix doesn't have an inverse, we cannot use the inverse matrix method of solving the simultaneous equations. We must use the method of reduction to echelon form to solve the equations. So, we've got the equations x plus 2y plus z equals 1, 2x plus 3y plus z equals 3, 3x plus 4y plus z equals lambda. If we use the first equation to eliminate z from the second and third equations, then we can take equation 2 and subtract equation 1, and that will give me x plus y equals 2. Similarly, we can take equation 3 and subtract equation 1, and that will end up giving me 2x plus 2y equals lambda minus 1. We're now going to use the new second equation to eliminate y from the new third equation. So if I want to eliminate y from the new third equation, I'm going to have to take the third equation and subtract twice the new second equation. If I do that, I've got 2x take away 2x, and it's important at this stage that I said I wasn't trying to eliminate x, so 2x take away 2x is 0x. I was trying to eliminate the y's. So the fact that 2y take away 2y is 0, I'm really happy about, because the whole aim of this was to eliminate the y's. Then I've got lambda minus 1, take away 2 times 2, gives me lambda minus 5. Now this equation 0x equals lambda minus 5 will only have solutions if the right hand side is 0. So 0x equals lambda minus 5 is an impossible equation unless lambda equals 5. If the equation 0x equals lambda minus 5 is impossible, then the equations are inconsistent. So for the equations to be consistent, we must have lambda equals 5. If we've got lambda equals 5, then the equation 0x equals 0 means that x can be absolutely any number that we like. So let's suppose that x is equal to alpha. Then the equation x plus y equals 2 tells me that y must be 2 minus x. In other words, y must be 2 minus alpha. The equation x plus 2y plus z equals 1 tells me that z must be 1 minus x minus 2y, which is 1 minus alpha minus 2 lots of 2 minus alpha, which simplifies to z equals minus 3 plus alpha. So the solution is x is equal to alpha, y is equal to 2 minus alpha, and z is minus 3 plus alpha, where alpha can take any value at all. Geometrically, this means that the three planes intersect on the line r equals 0, 2, minus 3, plus alpha times 1, minus 1, 1. Our final example asks us to investigate the intersection of the planes 2x plus y minus 3z equals 7, 4x minus y plus 2z equals 9, and 10x plus 2y minus 7z equals 35, and hence describe the geometrical relationship between the three planes. We've no idea at all whether these three planes are going to intersect in a point, in a line, or not at all. So the safest way of proceeding is to proceed with the reduction to echelon form method. So we've got our three equations. It's quite easy to eliminate y using the first equation. We can eliminate y from the second and third equations relatively easily. So, to eliminate y from the second equation, we could take the second equation and simply add the first equation. And if I do that, I'm going to get 6x minus z equals 16. To eliminate y from the third equation, using the first equation, if I take the third equation and subtract 2 times the first equation, then that is going to give me 10x take away 4x, which is 6x. The 2y take away the 2y gives me 0, exactly as we desired. And then I've got minus 7z minus 6z, which gives me minus z, equals 35, take away 14, which is 21. We can now eliminate z from these two equations by simply subtracting the new equation 2 from the new equation 3. And if we do that, we're going to end up with 6x take away 6x, that's 0x. Then we've got minus z minus z, which gives me no z, but I'm not going to write that down because the reason for us doing this subtraction was to eliminate the z's. So we've got 0x on the left hand side equals 21 take away 16, which is 5. So we've got 0x equals 5. Now that's impossible. So that means that the three equations that we've got are inconsistent. There is no value of x, y and z which satisfies all three of those equations at the same time. If we consider the normals to the planes, then the normal of the first plane is the vector 2, 1, minus 3. The normal for the second plane is 4, minus 1, 2. And the normal of the third plane is 10, 2, minus 7. None of these normals are parallel to each other, so the planes are definitely not parallel to each other. And if the planes are not parallel to each other, but don't meet, then we've got a situation where the three planes form a wedge or a tent type shape. So there's no point where all the planes meet each other.